Hello, my dear children. Welcome to the mathematics class. Today we are going to discuss probability. In the previous class, we have discussed some concepts of exercise 11.1. In that exercise 11.1, we have discussed how many approaches are there to study probability. To discuss probability, there are three types: classical theory of probability, statistical approach of probability, and what we are studying now is axiomatic approach of probability. Means to find the probability of an event, we use here set theory. Okay, mainly we use here our previous knowledge of set theory to find the probability of an event. In the statistical approach of probability, we use statistical data to find the probability of an event. Understood this difference, my dear children? Right. In the previous class, we have discussed what is meant by a random experiment and what is meant by outcomes of a random experiment and what is meant by a sample space of a random experiment. I hope you have understood all these concepts well. I hope you have done the first 5 sums in the exercise 11.1. Haven't you, my children? Right. In this exercise, let us discuss some more concepts related to axiomatic approach of probability. Okay, my children? Right. Event. What is meant by an event? We have studied about random experiment and sample space associated with an experiment. The sample space serves as an universal set for all the questions concerned with the experiment. Okay, my children. Yes or no, my children? In the previous class, we have discussed what is meant by random experiment and what is meant by sample space associated with the experiment. And the sample space is considered as a universal set of all the events related to that experiment. Okay, my children? Right. Consider the experiment of tossing a coin 2 times. An associated sample space S is equal to set HH, HT, TH, TT. So now, this is a sample space of the experiment of tossing a coin 2 times. So now, my children, in the previous class, we have written the sample space for this random experiment of tossing a coin 2 times. Okay, my children, understood this point? Right. Now, suppose that we are interested in those outcomes which corresponds to the occurrence of exactly one head. Okay, my children, suppose if we are interested to find the outcomes which has exactly one head in these outcomes, out of these outcomes. Here, how many outcomes are there in this sample space? How many sample points are there? 1, 2, 3, 4. 4 sample points. 4 outcomes. Yes, so my children, out of these 4 outcomes, suppose if we are interested to find the outcomes which corresponds to occurrence of exactly one head. And then what are the favorable outcomes out of these 4 outcomes, my children? Can you identify exactly one head? Yes, HT, TH. Yes, my children, these two only the outcomes which are favorable to our event, exactly one head. Yes, my children, right. We find that HT and TH are the only elements of S corresponding to the occurrence of this happening, that is event. Okay, my children, here these are all sample points, but out of these sample points we have selected only few sample points by taking some condition, that is the condition exactly one head. By taking this condition, we have chosen some sample points from the sample space. Then these two elements, these two sample points form a set. So this is called an event. Okay, my children. These two elements form the set E is equal to set HT comma TH. Understood this point, my children? What is meant by an event? Right. Now we know that the set E is a subset of the sample space S. Yes or no, my children? Similarly, we find the following correspondence between events and subsets of S. If you observe the previous example, you find out that E is a subset of the sample space S. Means an event is a subset of sample space S. Yes or no, my children? So here we discuss some events. Those are subsets of a sample space S. Okay, my children? Right. See here, my children, number of tails is exactly 2. If you take this event, then out of the 4 elementary events, 4 elements sample points, only TT, the corresponding subset of S. Yes or no, my children? Understood this event? Right. Now let us take another event. Number of tails is at least 1. That sample space we have to choose the elements which are having tails is at least 1. Means there may be 1 tail or there may be 2 tails. So these are the elements in that set S. Yes or no, my children? Similarly, number of heads is at most 1. At most 1 means number of heads should not be greater than 1. We should get to exactly 1 or less than 1. So here see, these are the elements in the set S which are favorable to this event. Understood this point, my children? Second toss is not head. This is another event. So from that set we can choose these elements. Second toss is not head means here see, this is the first toss, this is the second toss. So second toss is not head. Here also see there, second toss is a tail. Here also second toss is a tail. So like this we can define different events. Okay, my children. Similarly, number of tails is at most 2. At most 2 means tails may be 2 or less than 2. So see this one, HH means no tails are there. Here 1 tail, here 1 tail, here 2 tails. Understood this event, my children? This is also a subset of S. Okay, my children. Similarly, number of tails is more than 2. If the sample space if you observe the sample space, do you find the number of tails more than 2? No, we can't find any element in the set S. So that the tails is more than 2. So empty set. Understood these events, my children? These are the events, descriptions of these events. These are corresponding subset of sample space S. Understood, my children? Right. So the above discussion suggests that a subset of sample space is associated with an event and an event is associated with a subset of a sample space. Okay, my children, understood this point? Event means the subset of the sample space S. Here sample space S is considered as a universal set. The set theory is linked here. In the axiomatic approach of probability, we are linking the theory of probability with set theory. Okay, my children, understood this point? Right. In the light of this, we define an event as follows. Okay, my children, this is the definition of an event. Any subset E of a sample space S is called an event. Understood this point, my children? Understood this definition of event of an experiment? Yes, any subset E of a sample space S is called an event. Here sample space S means universal set of the experiment. Okay, my children? Understood this point? Right. Now let us discuss occurrence of an event. What is meant by occurrence of an event? Okay, my children. Right. Consider the experiment of throwing a die. Okay, my children. Let us take an experiment of throwing a die. Let E denotes the event a number less than 4 appears. Suppose let us denote an event E such that a number less than 4 appears on the die when a die is thrown. Okay, my children. Right. If actually 1 had appeared on the die, then we say that event E has occurred. Yes or no, my children? If you throw a die, if you die shows 1 up, what will you say? Yes, the event has occurred. If the die shows 2, what will you say? Event E has occurred. If die shows 3, what will you say? The event E has occurred. Yes or no, my children? Suppose if the die shows 4, what will you say? Yes, the event E has not occurred. If the die shows 5 up, what will you say? The event E has not occurred. Understood these points, my children? Right. As a matter of fact, if outcomes are 2 or 3, we say that event E has occurred. Understood this point, my children? On the die, if 1 or 2 or 3 appears on the die when the die is thrown, then we say that event E has occurred. Understood this point, my children? Right. Thus, the event E of a sample space S is said to have occurred if the outcome omega of the experiment is such that omega belongs to E. Okay, my children? Understood this point? Right. If the outcome omega is such that omega does not belong to E, we say that the event E has not occurred. Okay, my children. Here omega denotes elements of the set S. S is a universal set. Here omega denotes the elements of the set S. The elements belongs to X, belongs to the event E, then we say that the event E has occurred. If the outcomes means elements of the set S does not belong to E, then we say that event E has not occurred. Understood this point, my children? Right. Now let us discuss types of events. Okay, my children? Events can be classified into various types on the basis of the elements they have. Okay, my children? Here we are going to discuss types of events on the basis of the elements they have. Okay, my children? Right. Impossible and sure events. The empty set phi and the sample space S describe events. In fact, phi is called an impossible event and capital letter S, that is the whole sample space, is called the sure event. Understood this point, my children? What is meant by impossible event and what is meant by sure event? Yes. If we get an empty set, then we say that event is an impossible event. In the set E, if all the elements of the sample space S are included, then we say that event is a sure event. Okay, my children? Right. To understand these concepts well, let us consider the experiment of rolling a die. The associated sample space S is equal to set 1, 2, 3, 4, 5, 6. That's what I mentioned. Suppose let us consider an experiment of rolling a die. For this experiment, let us find out what is impossible event, what is sure event. Okay, my children. Then for this experiment of rolling a die, what is the sample space? Yes. S is equal to set 1, 2, 3, 4, 5, 6. These are all the outcomes when a die is rolled. Yes or no, my children? Yes, these are all the outcomes. These are all sample points. Okay, my children, understood this point? Right. Let E be the event. The number appears on the die is a multiple of 7. Can you write the subset associated with the event E? Suppose let us consider an event, and we denote an event as the number appears on the die is a multiple of 7. From these elements, can you find out the multiple of 7, my children? Right, we can't find any element which is a multiple of 7. Yes or no, my children? Right. Clearly, no outcome satisfies the condition given in the event. That is, no element of the sample space ensure the occurrence of the event E. Thus, we say that the empty set only correspond to the event E. In other words, we can say that it is impossible to have a multiple of 7 on the upper face of the die. Understood this point, my children? Thus, the event E is equal to empty set. E is an impossible event. Let us take up another event F. The number turns up is odd or even. Clearly, F is equal to set 1, 2, 3, 4, 5, 6. Yes or no, my children? That is nothing but sample space S. That is all outcomes of the sample space S. The experiment ensured the occurrence of the event F. Thus, the event F, that is equal to sample space S, is a sure event. Understood this point, my children? Which event is said to be impossible event? Which event is said to be a sure event? Yes. If you get an empty set, then the event is said to be impossible event. If the event is a universal set, then we say that the event is said to be a sure event. Understood this point, my children? Right. Simple event. Let us discuss now what is meant by a simple event. If an event has only one sample point of a sample space, it is called a simple or elementary event. Okay, my children. In the sample space, there are outcomes. Sample points are there. As I mentioned, there are sample points. Outcomes of the experiment will be there in the sample space. So, every outcome in that sample space is said to be every simple point. Sample point is said to be simple event or elementary event. Understood this point, my children? Right. In a sample space containing n distinct elements, there are exactly n simple events. Understood this point, my children? In the sample space S, capital letter S, if S has n distinct elements, then we say that there are exactly n simple events. In other words, the sample points of the sample space are said to be simple events. The sample points of the sample space S is said to be simple events. Understood this point, my children? Right. For example, in the experiment of tossing two coins, a sample space is S is equal to set HH, HT, TH, TT. Yes or no, my children? This is the sample space of the experiment of tossing two coins. Yes or no, these are the outcomes. These are the sample points in the sample space. How many sample points are there? 1, 2, 3, 4. These are 4 distinct elements. Yes or no, my children? These are all distinct elements. So all these elements are said to be simple event or elementary event of the experiment. Understood this point, my children? Right. There are 4 simple events corresponding to this sample space. Yes or no, my children? These are E1 is equal to HH, E2 is equal to HT, E3 is equal to TH, and E4 is equal to TT. These are all four distinct elements of the sample space S. So first element is one event, second element is another event, third element is another event, and the fourth element is another event. All these four events are said to be simple events or elementary events. Understood this point, my children? Right. So we have discussed what is meant by a simple event. Now let us discuss what is meant by a compound event. If an element has more than one sample point, it is called a compound event. Understood this point, my children? If an event has more than one sample point, then the event is said to be a compound event. Okay, my children? Right. Let us take an example to understand this concept well. For example, in tossing a coin thrice, in the experiment of tossing a coin thrice, the events E is equal to exactly one head appeared. Let us consider this is one event E. E is equal to exactly one head appeared. Okay, my children. F is another event. At least one head appeared. This is another event we define, and another event F as at least one head appeared. Okay, my children. Next, another event G is denoted as at most one head appeared, etc. Here we have defined three different events, E, F and G. E is defined as exactly one head appeared, F at least one head appeared, G at most one head appeared. Like this we have defined the events of this experiment of tossing a coin thrice. Okay, my children? Right. These are all said to be compound events. Okay, my children? These are all compound events. The subset of S associated with these events are is equal to HTT, THT, TTH. Okay, my children? Yes or no, my children? Only few elements are selected from the sample space S. This is one event E. This is a compound event. Only few elements were selected from the sample space S. Understood this point, my children? Similarly, F is equal to, see here at least one head appeared. So HTT, THT, TTH, HTT, HTH, THH, HHH. These are all the favorable outcomes to the event F. This is also a compound event. Means a subset of S, capital letter S. Okay, my children, understood this point? Right. Now come to the event G. What is the event G? At most one head appeared. Means there may be one head or no head is appeared on the tosses of the coin. So here TTT, THT, HTT, TTH. Okay, my children. In the sample space, how many elements will be there? How many elementary elements? How many sample points will be there? 8 elementary events will be there. Yes or no, my children? Out of these elementary elements, 8 events, 8 elementary events are there. Out of the 8 elementary events, we have selected only few elements. For F also we have selected only few. Here also we have selected only few elements. So these are said to be compound events. Thus, these are also subsets of sample space. Yes, but the difference between the elementary events and compound events is, see, observe here, how many elementary events are there? 2, 3 elementary events are there. But in a simple event, there is exactly one sample point. But here 3 sample points are there. Observe here, how many sample points are there? 1, 2, 3, 4, 5, 6, 7. We have selected 7 sample points. Out of 8 sample points in the sample space S, we have selected 7 sample points. Similarly, here 1, 2, 3, 4. 4 sample points were selected from the sample space S. Understood these points, my children? Each of the above subsets contain more than one sample point. Hence, they are called compound events. Understood this point, my children? Right. These are all said to be compound events. Now let us discuss algebra of events. In the set theory, we have discussed algebra of sets. Yes, sir, no, my children. In the chapter sets, we have studied about different ways of combining two or more sets, which union, intersection, difference, complement of a set, etc. Likewise, we can combine two or more events by using the analogous set notations. Okay, my children. Here also we are using the set theory knowledge for algebraic events. Okay, my children. Right. Let A, B, C be events associated with an experiment whose sample space is S. Okay, my children. Let us consider these are the three events. These are the three sets in the sample space. Yes, in the universal set. Yes, these are three sets. Okay, my children. Right. Now come to the definition. Complementary event. For any event A, there corresponds another event. Yes, sir, no, my children. A dash called complementary event to A. It is also called the event not A. Understood this point, my children? What is meant by complementary event? The set theory we have discussed complementary set. If A is a set, then A dash is said to be complementary set of this A set A. Similarly here, if A is any event in the sample space, yes, then A dash is said to be complementary event or not A. The event not A. Understood this point, my children? What is meant by complementary event? Right. For example, take the experiment of tossing 3 coins. Okay, my children, let us take this experiment of tossing 3 coins. Right. An associated sample space is S is equal to set HHH, comma HHT, comma HTH, THH, HTT, THT, TTH, TTT. Okay, my children, these are all the outcomes when a 3 coins are tossed simultaneously. These are the 8 outcomes. These are the 8 sample points in the sample space. Yes. Okay, my children, understood this sample space? Yes. For this random experiment, right? Let A is equal to HTH, HHT, THG. Be the event only one tail appears. Yes, sir, my children. If we observe this event, in all these events, T appears only once. Yes, sir, my children. Only one tail appears. Yes, sir, my children. Right. Clearly, for the outcome HTT, the event A has not occurred, but we may say that the event not A has occurred. Thus, with every outcome which is not in A, we say that not A occurs. Okay, my children. Out of these 8 elements, we have chosen only 3 elements for the set A. How many elements were left here? 5 elements. Yes, sir, my children. So the remaining 5 elements are said to be complementary event of event A, that is A dash. Understood this point, my children? Right. Thus the complementary event not A to the event A is A dash is equal to set HHH, comma HTT, comma THT, comma TTH, comma TTT. Observe, my children, here the remaining 5 elements from the sample space S was selected. These are form complementary set of A, complementary event of A. We don't say here set, event. Okay, my children, that is only the difference here. Okay, my children, or A dash is equal to set of all omega such that omega belongs to S and omega does not belong to A. That is equal to S minus A. Understood this point, my children? Complementary set definition we used here. Set theory concept were used here in the axiomatic approach of probability. Understood this point, my children? Right. Now the event A or B. Recall that union of two sets A and B denoted by A union B contains all those elements which are either in A or in set B or in both sets. Yes or no, my children? Do you remember the definition of union of two sets A union B? What is meant by A union B? The set of all points. The set of all points which are in either A or in either B or in both sets. Then the set is denoted by A union B. Yes or no, my children? Right. When the sets A and B are two events associated with a sample space S, then A union B is the event either A or B or both. This event A union B is also called A or B. Understood this point, my children? Event A or B means A union B. Okay, my children, understood this point? Event A or B means A union B. We have to find A union B. From the sample space S, we have to find A union B. Therefore, event A or B is equal to A union B. That is equal to set of all omega such that omega belongs to A or omega belongs to B. Okay, my children, understood this point? Now let us discuss the event A and B. Okay, my children, we know that intersection of two sets A intersection B is the set of those elements which are common to both A and B. That is, which belongs to both A and B. Do you remember this concept of intersection of two sets, my dear children? In the set theory, we have already learned A intersection B denote the set of all points which are common to the both the sets A and B. Yes or no, my children? Yes. We apply the same concept. As I said, we are studying the probability in the axiomatic approach, means by using the set theory. Okay, my children? Right. We use the same concept to the events also. If A and B are two events, then the set A intersection B denotes the event A and B. Thus, A intersection B is equal to set of all omega such that omega belongs to A and omega belongs to B. Understood this definition, my children? We are connecting the set theory. We are connecting the set theory to the events also. Suppose if A and B are two events. In the case of set theory, we assume that these two A and B are two sets. But here we are assuming that these are two events. Then A intersection B denote an event, that is A and B. Both events occur at a time. Understood, my children? Thus, A intersection B is equal to set of all omega such that omega belongs to A and omega belongs to B. We wrote this event in the set builder form. Understood this step, my children? Right. Let us take an example to understand this concept well. In the experiment of throwing a dice twice, suppose a die is thrown twice. Okay, my children, let us take the experiment. Okay, my children, right. Let A be the event. Score on the first throw is 6. Let us denote an event A as score on the first throw is 6. Okay, my children, right. And B is the event sum of the two scores is at least 11. Understood this event, my children? This is event A and this is event B. Two events are defined here. Okay, my children? Right. Then A is equal to, what are the ordered pairs? What are the outcomes favorable to event A? Yes, ordered pair 6, 1, 6, 2, 6, 3, 6, 4, 6, 5, 6, 6. Understood these outcomes which are favorable to event A, my children? Actually, in the sample space, there are 36. 6 into 6. Previously, we have discussed that point, my children. If we die is thrown twice, then we get totally 36 outcomes. Out of the 36 outcomes, these are the favorable outcomes to the event A. Understood this point, my children? Understood this step? Right. And B is equal to ordered pair 5, 6, 6, 5, 6, 6. So A intersection B is equal to, what are the elements which are common to the both sets A and B? Yes, 6, 5, 6, 6. Understood this set B, my children? Event B. Here we don't say, here set B, event B. What are the outcomes favorable to event B? Yes, because the score on the two dice should be at least 11. So there may be 11 or 12. So 5, 6, 6, 5 and 6, 6. These three are the outcomes favorable to event B. Understood this step, my children? Right. After finding the two events, let us find which are the outcomes common to both events 6, 5, 6, 6. Yes or no, children? This is the event A intersection B. Understood this point, my children? Right. Note that the set A intersection B is equal to set 6, 5, 6, 6 may represent the event. The score on the first throw is 6 and the sum of the scores is at least 11. Understood this event, my children? If you want to say this event in terms of words, this event denotes score on the first throw is 6 and the sum of the scores on the two dice and the two times is at least 11. Understood this sentence, my children? Right. Now let us define another event A but not B. Okay, my children, we are defining this event A but not B. We know that A minus B is the set of all those elements which are in A but not B. Therefore, the set A minus B may denote the event A but not B. We know that A minus B is equal to A intersection B dash. Understood this definition, my children? The event A but not B. Event A occurs. Event A happens, but event B does not happen. Then we denote this event as A minus B or A intersection B dash. Here also, if you observe, the set theory was used. Okay, my children. So we know that A minus B is a set of all those elements which are in A but not B. Do you remember this point, my children? From the set theory, we have learnt this point. Yes or no, my children? Right. Therefore, A minus B denote the event. Here we don't say this is a set. It is an event. A but not B means event A occurs but event B does not occur, does not happen. Okay, my children. And moreover, A minus B is equal to A intersection B dash. This is also from the set theory. We can denote this event as A minus B or A intersection B dash. Both denote the same event. Understood this point, my children? Right. Now let us take an example to understand these concepts well. Okay, my children. Right. Consider the event of rolling a die. Let A be the event getting a prime number. B be the event getting an odd number. Write the sets representing the events A or B. Second question, second part, A and B. And third part, A but not B. And fourth part, not A. Understood all these events, my children? Here an experiment is given. What is the experiment? Rolling a die. Can you write the sample space for this random experiment of rolling a die, my children? Yes. S is equal to set 1, 2, 3, 4, 5, 6. Yes or no, my children? For this experiment, sample space is 1, 2, 3, 4, 5, 6. Now, some events were defined, A and B, namely two events, namely A and B are defined like this. A be the event getting prime number and B be the event getting an odd number. Understood these two events, my children? Then can you tell me the elements in the set A? Getting prime number means what are the prime numbers? 2, 3 and 5. Yes or no, my children? Getting the odd number, can you tell me the elements in the set B? 1, 3, 5. Yes or no, my children? Understood this question? Right. Now we have to write A or B, A intersection B, A but not B, not A. Okay, my children? Right. Now come to the solution part. Here S is equal to set 1, 2, 3, 4, 5, 6. Yes or no, my children? Right. A is equal to set 2, 3, 5 and B is equal to set 1, 3, 5. Obviously, understood these three sets, my children? This is a universal set, sample space, and B is A is another set or another event. B is another event or B is another set. Then obviously, first question, come to the first question, A or B. What is meant by A or B? A union B. We had to find intersection union of these two sets. Then what are the elements in the A set A union B? 1, 2, 3, 5. Okay, my children. Do we remember the union of two sets concept, my children? We use the same concept here to find the event A union B. Understood this event A union B, my children? Right. Now come to the second part of this question. A and B. What is meant by A and B? Yes, A intersection B. What are the elements common to both the sets A and B, both the events A and B? Yes, 3, 5. Only these two elements are common to both the sets or both the events A and B. Understood this step, my children? Right. Now come to the third part of the question. A but not B. How do you denote this event? A minus B. Do you remember the difference of two sets, my children? Yes. So 2, 3, 5, 1, 3, 5. Here 3, 5, 3, 5 gets cancelled. What is the element left in the first set? 2 only. Only one element. So set 2. Understood this step, my children? Right. Now come to the last part of the question. Not A means A complement, that is equal to S minus A. Yes or no, my children? Use the same set theory concept here also. So yes, in the set theory, A dash means A complement means mu minus A, universal set minus A. But in the case of probability, we write S minus A because here sample space is considered as a universal set. Okay, my dear children. So S minus A. So what do you get? S minus A, 2, 3, 5 gets cancelled. 1, 4, 6. Understood this step, my children? Right.